Today we're going to carry on our discussion on chapter 4, which is going to be the pipelining. So we've already discussed the basic of logic design. We discussed the appendix A, which was some preliminary things about how to write Verilog, and you're seeing it in your labs. And then the final section of chapter 4 would be how to do the pipelining process, which is a very important aspect of computer architecture. So I personally loved seeing this when I was an undergrad and grad student. And that was the first thing that attracted me towards computer architecture. So you can see it yourself. If you like chapter 2 more, perhaps you're sort of a coder kind of guy in computer science. If you are chapter 4, you love these new set of pre-labs, perhaps logic and hardware suits you better. If you like this kind of notions of how to optimize a pipeline and how to optimize performance and evaluating performance, so perhaps numerical analysis, optimizations, and evaluations, suit you better if you want to do your, undergrad thesis or later on your master. Any questions? All good? All right. So, think about a pipeline analogy as a 4-stage of, things you want to do in order to clean your clothes. Okay. So, in order to clean your clothes, what you're going to do? So, they are shown here in these figures. First, you have to wash them, right, in blue. Then you have to perhaps dry them and then bring them out and fold them and then put them back in their place, right? Think about them as 4 discrete processes, okay, that they should be done one after another in sequence, right? Say you have, and I'm sure that you have one set of these equipments available, like one washer, one dryer, one set of hand to fold and then putting back in place wherever they were. So if you put them, if considering that each of those tasks takes half an hour, right? You start washing from 6 p.m. So it's going to end at 6:30. You start drying at 6:30, and drying would take another half an hour. It's gonna take up to 7 p.m. right? And then later on, you have to fold them half an hour and then put them back in your closet. Okay, so for half an hour, it's gonna take 2 hours to finish these 4 tasks. Okay, 2 hours. So this was the very early notion of running things, executing things on your hardware in the 50s and 60s. So you did, I don't know, in the case of computer architecture, you wanted to understand which instructions needed to be executed first, right? You have to fetch the instructions ID, and then you need to decode that instruction if it was needed to be decoded, so say another task. Then you need to execute that instruction. If it was a load instruction, you needed to load something to the memory, so you would have need to access memory. And then finally, you need to write back the new results, right? So think about these discrete stages as some stages that your processor in computer do, okay? So how are we going to optimize this process? For sure, the easiest way is like just putting them sequentially. First, I have to just wash, dry, fold, and put back, okay? So say you are living with your 3 other roommates, and all of you have to do the same process, right? So if you are the last guy that got your hands on the washer, so you need to first wait for like the rest of the 3 first, right? So you have to wait for 2 hours to start working your washing process, okay? So researchers in computer architecture came up with the notion of pipelining. So let's see, what does a pipelining mean? So in general, pipelining, which you can see in the bottom figure, is an implementation technique in which multiple instructions or processes, just like here, are overlapped in execution, right? Although we have the same amount of resources, but the way we pipeline them here, it's as if we can run them in parallel. Not completely, but almost. They're overlapping their execution, okay? So if going back to the analogy of the laundry, so if you make it in pipeline, what's gonna happen? So your roommate A will start the washer, right? So the washing machine is in use. So you have to wait at least for half an hour for that. While he picks up his clothes and put it in dryer, now the washing machine is available, right, for your roommate B, and he's going to use it at this level. So while A is doing drying, you can do the washing, right? And then after this one passed, on the third level, after 2 half an hours, so like 1 half an hour, 2 half an hour, 3 half an hour here, now the drying would be also available for the first one, because, I'm sorry, folding would be available for the first one because his drying has already finished. Again, your washing machine for the second guy is finished. So for the third person, he can use the washer at the same time that roommate A is doing the folding, roommate B is doing the drying, okay? The fourth half an hour, when your first roommate, number A, is putting back his clothes in a closet, the fourth one is having a chance to start the washing process, okay? So although it took this amount of half an hours, so 1, 2, 3, right, to fill up the pipeline, so this is the term we use in computer architecture. So normally filling up your pipeline takes some stages depending on the number of cycles you have and the task. But after the third one, so in the fourth cycle, you see that at the same time, all 4 of you are using something. So you are utilizing something, and this is efficient. So we are, in computer architecture, we just we are considering efficiency. We want to use all of our resources in a way that none of them are idle, because we are speeding up execution of so many different instructions that are running in a processor, okay? So it took us 3 half an hour or 3 cycles, but at cycle number 4, all of the resources are getting used. Just like that, when we are winding down the pipeline, it's going to take us 3 more cycles that the tasks that were already in the pipeline gets done, okay? So the first guy finishes folding, and then another half an hour, and so up to here, all of those 4 guys have already finished their 4th task. So now, take a look at this. You started at 6 p.m. in a sequential mode, and 4, 4, 4, 4, so it took up to 2 a.m. to finish that, right? 2 hours, 2 hours, 2 hours, 2 hours. So it would take 8 hours in sequential mode. Now you started at 6 p.m. and all of the task is done, right? 9:30. You see, there's a huge difference between having a pipeline or complete sequential, and that's the difference you see here. So 4 loads in sequential mode, 8 hours. In pipeline mode, 3 hours and a half. So the speed up would be this divided by 3.5. So above 2 and 2.3x, like times, you're having speed up, right? So what would be the best scenario here? So the scenario would be that you don't stop for anything. Everything was completely used, no pipeline filling, and then no winding down, right? So in the best case scenario, if you had 4 instances of all of those, you would have a speed up of 2 because all the tasks would have been in parallel, but you don't, because you are filling up the pipeline. Depending on the number of stages, you are losing some portion of that 4x speed up, right? And you're settling for 2.3. So that would be the ideal case, 4x speed up, but now you're having 2.3x speed up, okay? Because the number of stages you have here takes to fill, and then you have just four different lines of task. If you had like 2,000 lines, this would have been closer to 4. because you would have used more of the pipeline notion. All right, so that's the general formula. If you want to compute the upper bound of a non-stop or a full pipeline, it's going to be 2n divided by, so that's each of your tasks here, half an hours, plus 1.5 of the 3 stages. All right, so that's the analogy of a laundry in a pipeline. So let's see what are the stages in a computer architecture. Yep.
What does N mean?
Is a number of tasks or number of cycles. Both of them are 4 here. So in RISC-V, just like MIPS, the other famous architecture, we have 5 different stages in a pipeline. Okay? So they're called IF, instruction fetch, ID, instruction decode and register read. X is the execution instruction, or the cycle that does the execution, right? You execute the operation or calculate the address. Mem is the access memory operand, so that's the stage for that, stage number 4. And last stage, the number 5 is write back, WB, write results back to register. So we're going to use these a lot in this latter stage of chapter 4. So instruction fetch, decode, execution, mem, write back. Okay. So now let's see how we're going to, generalize that analogy towards RISC-V and our architecture. So assume each of the time for stages are written here. So 100 PS, so picoseconds for register read or write, 200 for other stages, right? These memory, ALU, and fetch. But read and write, so these two, so this is 100, this is 100. These are 200, okay? And these are different tasks or line of codes that you need to run, okay? So if you add them, right, you're gonna come up with these numbers, 200, 100, 200, 200, 100. It's gonna be 800 for a task of a load. For a task of a store, if we were to run it in a single cycle, sequential manner, right, you would have 200 for this and plus all the rest. For the store, you don't need a write back because you've already stored it here. That's the difference between a store and load. And just like that, for R format, can anyone recall what R format was? Add, subtract, multiply. So why we don't have this memory stage for that? What is it?
We're just getting it from the register.
That's right. We are getting it from register. We are not accessing the memory at this point. So that's why this is a sort of a don't care, or we're not going to use this also for that. So an R format instruction would take around 600 PS if we were to assign 100 and 200 for these different stages, right? And for branch, we also don't need to access the memory and write back. We just have to decide at the end of the ALU if you want to branch or not, right? Whether the branch is taking or not. So in a sequential manner, it would take 800 PS for a load, 700 for store, 600 for an ALU type format, and for branches it would take 500. Okay, so now let's make it pipeline and see what's going to happen. So in a single cycle, it would be pretty easy. You just have to wait for the finish of the first one completely. So the first load x1 up to the address of 100 of x4, right? You have to do the IF, you have to do the ID, X, mem, and write back. Okay, all those 5. You have to wait up until this one finishes, and then you go for the next load. It would take another 800 of its own, another instruction fetch ID XMW back, right back, okay? And then you will have to start the third load. So 1 800, 2 800, up to here. So each cycle here would have taken, each complete single cycle would have taken 800, okay? So now let's look at the other way. What if we make it in a pipeline? All right? So now some of my cycles are not taking the same amount of time as the others. So some of them are taking 200, some of them are taking 100. So 100 would be a smaller chunk here. That's why we leave this here as if the processor doesn't do anything, right? So it would only take 100 here up to this point. So while we fill up the pipeline with the first instruction, the first load x1, comma 100 x4, right? On the next cycle, so while this one goes to ID, the first one starts its IF, okay? And it goes up to finish its own instruction. While it goes to its ID, the second one, the third one starts at IF. So while at the same time that the third starts its IF, instruction fetch, the first one is doing the execution, okay? So you add them, now you have to look at them this way, from here up to the point they're finished, okay? And that's going to be the overall pipeline up to this point, right? Okay? But each of those only take 200 because you have to take the highest amount, the lowest sort of stage that would take to run, which is among 100 and 200, it would be 200. So the rest should wait that 100 to match the cycles. If all the cycles were having the same amount of time, so all of them would be equally. Any questions? No.
Why does there have to be a gap between the instruction fetch and the register?
Because that register is in ID, right? And you see here in ID they're taking 100 based on the question. Some of the stages are taking 200, some of them are taking 100. So because of that, the rest should wait that 100, okay, to match the timing.
To match what time?
Because now, so say you are running with your friend, okay, you are a faster runner, but you wanna make sure you're running together, okay? So you have to just, if you run with your same pace, you have to wait for this guy to reach you. Again, you have to run and wait for this guy to catch you because you want to run together, okay?
Yeah, but like, how does that like apply here? Because either way, the preceding task always starts before the next one. Like if you could go back to the slide after this, like why isn't it possible to push the register read and ALU data access all the way back by 100? Does it create any error or something?
No, you can stall. We'll discuss stalling in pipelining in a moment.
Yeah, because
you can stall execution of any instructions.
Yeah, I'm saying that because if you do that the second time and you do that the third time, that will reduce the entire duration by like let's say 100, I think.
Yeah, but you are because you're okay. That was a very good question. All three instructions are load, right? All of them are homogeneously load. If the second and third wasn't load, right? And you would have needed the output of the load for the second instruction, another store or a branch, you would have to wait. But to make it simpler, we install all of them, okay? Very good question.
Same question.
Okay, very good question as well. Any other questions?
Is there a benefit to running the one at the top and the one at the bottom?
The single cycle mode?
Yeah.
The single cycle mode doesn't have any benefit except its simplicity. You don't have to take care of anything. You just wait for all of the instructions to finish one by one, right? So the way we graded your midterm paper was in a pipeline. So I started assigning the first question to your first TA. Okay, after the first TA finished, I passed it to the second one, right? And then I was just continuously adding these third, fourth, and fifth to other TAs. So while the pipeline was filled, everyone was doing his own job. Okay, so you think about pipelining in your life. You can benefit from optimizations, right? In many ways.
If the second instruction is not a load, it's a if or something, that will use the first instructions. Register read, can we do the pipeline?
Yes, we can, but we have to consider some stuff which we will see in a few slides. Good. Other questions? Okay. So now let's see how we're going to calculate the pipeline speedup. So if all the stages are perfectly balanced, right? If all of them would have taken the same amount of time, so the time between instructions in a pipeline manner, right, would take a fraction of the non-pipeline manner. And what was the fraction? It was the number of stages that you would have considered, right? We have 4 stages here, or 5 stages in RISC-V, so you would have to divide it to 5. If they are not balanced, just like what you saw here, they're not balanced. So the speed up will decrease because you have to wait at some point in order for others to catch you up. Okay. All right. So RISC-V, the hardware has been designed already for pipelining. So when you run instructions on the hardware, automatically it fills up its pipelining in hardware and runs that. You can do also pipelining while you're coding, right? In any languages, you can just Google like Java, pipelining in Java. You can just process your stuff in a pipeline manner, or in C or C++. So this can be done also in software mode. But RISC-V in architecture mode, so the hardware should be able to take care of that at the hardware level, right? So no matter what you pass, using the compiler knowledge is going to be able to run that on a hardware. All right? The other thing is, one of the other simplicity in RISC-V architecture is all of those instructions in RISC-V are taking only one cycle. Okay? So whereas other more complex architectures in x86, which Intel machines using, up to a certain point, perhaps 2015 or 16, they were varying in number of cycles they would need to complete their instruction, right? So that would decrease some performance out of that. Okay, so coming back to your friend's question, pipelining is very good. It's awesome. You can gain from speed up depending on the number of stages and the job you have. However, that will bring up 3 main category of difficulties, right? Issues. We call them hazards. So 3 hazards here. First of all, it's a structural hazard. So when you don't have enough of hardware to assign that sort of instruction to run, so that's going to be a structural hazard. The other one is a data hazard. So sometimes you want to access a data which hasn't been ready for you, or you wanted to branch, but you don't know the output of the previous one, and the previous iterator, like, I don't know, it was, if you hit the I was 20, you can branch, but you don't know if I is 20 or 19, so you have to wait for the previous instruction to update the I, so you know what I is, and then based on the value of I, you branch, right? So that's control hazard. The second one, a data hazard. You want to store something which you haven't already accessed by loading it, okay? Or you want to add 2 values, you don't know the first one. So these are data hazards. So in high level manner, so you have 3 different issues or hazards with pipelining. Okay, we're gonna see them one by one here. Okay. So while we face hazards, what we can do is, because we are no longer able to run the pipeline with the same speed it was running, we have to stop the pipeline. We have to halt it for a second, for a cycle, right? And then the notion we use here is we put a bubble there, right? In computer architecture, we call it we stall the pipeline by a number of cycles, 1, 2, 3. It's as if we are putting bubble or no operation. Sometimes we call it NOP. So NOP is like no operation, or just you put bubbles. It's like the system. Some of the stages don't have to do anything. They just have to be idle, wait for the other to bring up the results for them. Okay. So let's see what are those. Okay. All right. So a very easy example. So you have two instructions. One is add, the other one is sub. Okay. So you want to add x19, x0, and x1. Okay. However, the next instruction in a pipeline, it's subbing that x19 and x3. Okay. If you put it in pipeline, so while my add was running, while instruction fetch was finished, at this point I wanted to start my if id x mem and write back of my sub. Okay. So add is adding these two. So after execution and before the memory, so at this point, at earliest, I would have known the answer for this. But still, I had to wait for write back, right? At this point, I knew what the value of updated value of x19 is, so I can use it. But here, at the instruction fetch, I'm fetching that, oh, I need to run this code, so I need to access them. But where are they? I don't know, so I have to wait. You make a bubble, no operation, no operation, no operation, up to 3 stages, so that this becomes up to here, right? So 1, 2, and 3. That's why instead of putting 3 here, you put 3 lines of bubble this way to make it easier for you. So this is as if we are waiting up to here, and then now we are accessing it here, okay? So you need to put 3 stalls or bubbles here, okay? Everyone understood why we have 3 here? Because at LES, we need to decode that, and we need the result of the write back of the previous one. We can fetch the instruction, but we cannot do anything. We have to wait for that. All right? So that's why this write back of the previous one should be finished, and so that we start the ID of the next one. Okay? That means that I'm losing 3 cycle of my pipeline. I have put 3 bubbles, or 3 stalls, or 3 nopes, so I can carry on the pipeline the way it was. Is it clear?
Professor, how are you putting the bubbles? Can you explain it once more?
So this way it's as if you're just, you want to start it right here, okay? You want to start, so the IF would be here, ID would be here, X, mem, and so here, instead of starting it here, now you have to start it here, okay? How many of them are here? Is 1, 2, and 3. Okay, instead of writing down underneath, we put 3 lines. The other way would be just, you start the first 5, and then instead of starting the second one, you're starting in here. Right, so that was your number 1. So number 2 won't start here, and it's gonna start here, because you put nope, nope, and nope here. Okay, you started here. 3 bubbles. Okay, it's as if you ran 3 bubble lines in a pipeline. Okay, both of them are the same. Let me just clear this mess here. Okay,
essentially only like one step faster than sequential this way?
If we were having only 2 instructions and 5-stage pipeline and only 2, yeah. In this case, yeah. Up to now, yes. Yeah.
Why can't you fetch the instruction first and then you stall it? Does it have to always run like all together?
No, we can do that actually. Yeah, we can do that. So now, now we see depending on the type of the instruction and the features that your hardware is giving you, now we see how we're going to implement solution that we can reduce this 3 to 2 to 1 or even 0, okay? All right. And those that are half colored, it's because half of the cycle you're reading, half of the cycle you're writing, okay? And each of them are having their own story. Yeah, we talked about earlier in chapter 4. Okay. Now, instead of 3 stall or 3 bubble, now we're gonna find a way to make 2. Why? Because as your colleague mentioned, we can fetch the instruction. We know what the line is, right? We know that we have to do sub x2, x19, but and x3, but we don't have the values available. Okay, so no matter what, I can fetch it, right? I can fetch, so at least I'm avoiding my 3rd bubble, so to make it to 2. So now I can fetch it. So while this one is going on, I can fetch this. So while the write back was finished, I can just start the idea at this point, okay? Now, so now I reduce from 3 to 2 here. Now let's see what else could have been done. In many of the recent hardwares, there is another feature called forwarding or bypassing. So in general, when you do an add instruction, right, after your execution stage, you actually had the result. You just wanted to write it in memory, right, and then write it back. But at the same time, that bus on your hardware, while it was having the results available after X, right, it would be as if you could have used this one right away. Right? So instead of waiting to be placed here, and then you fetch it from here, you could have just get another branch and then, oh, could you pass it to me at the same time? So could you forward the result you generated at your X stage right away, so at my ID I can use it, okay? So this feature in hardware is called forwarding. And depending on the type of instruction, you can forward either after X, but for load instructions, you only have the data available after mem, so you can forward only after memory stage. So depending on the type of the instruction, you can forward either after X or mem. Okay? So now, at this point, if I have the forwarding, I can just run it right away. I don't have to install anything. But the cost requires an extra connection in the data path, right? So I can forward the result of the first stage execution to next stage ID. Okay, does that make sense?
Are we gonna get more Verilog questions or RISC-V questions on the exam?
I was very related to what I've been.
So
Is it? Are you in the class? Where are you in the class?
yeah,
So are you talking about the finals?
yeah.
Verilog questions in final? You might have. Yeah.
No, which ones are we gonna get more?
Okay, we can talk about it offline. Any other questions? All good? Everyone understood the notion of forwarding? Good. All right. So, as I mentioned, for the forwarding, we can do it right after X execution stage for add operations. But what if that operation was load, right? So we only we only get to know the value of the load after the memory. So even if with a pipelining and a forwarding, right? If we were to access this after a load instruction instead, right? We would have need one set of stall, one set of bubble here, because we would have to wait so that my ID becomes after mem, right? Otherwise, I didn't have access. So after execution, there's no value available of the load because I haven't fetched it. Okay? So for load instructions only, we can't always assure that without any stall or without any bubbles, we are able to run that in a pipeline. Okay? Any questions? All right. So another intuitive optimization you can do is sometimes when you write your assembly code, okay, you can just take a look at your assembly code and see, I might be able to reorder my assembly code on the left side so that I can avoid stalling or putting bubbles in my pipeline, as long as they're not needed, right? So say if you are doing these two additions, right? It doesn't matter if you just do this one and this one, or this one first and this one first. I'm sorry, this one first. Let me just get rid of this. It doesn't matter if you do this one first and then F first, right? And then this one first and this one last. You can, because none of them are interdependent. So you can reorder this. So to avoid to have the need to access X2 right next to each other, okay? The way we've been implementing it on the left side is we are loading the first one, loading the second one, which is the X2, and then right after that we're gonna add to generate this result for A, okay? That was this. If you reschedule it this way, you have to wait at least for one bubble or three without a forwarding. Just like that for the addition of these two to make this. But if you reorder and you load all of them F together, so that's a chunk of the load, and then you add them and store them, you see these X2s are far the furthest that possible, so that we don't need to bubble or stall anything. Okay, this is called rescheduling or reordering. This is very well known in compiler, but sometimes you can do it by hand when you want to optimize the code to make sure that you can utilize the full potential of a pipeline. Okay, so you see, using this way, now you need 13 cycles. You reordered and you reduce it to 11 cycles. The same operations, same hardware. You optimize it yourself, right? But just reordering these two. Is it clear? Questions?
I sort of zoned out. Could you explain it again?
Reordering?
Yeah.
So we are trying to find a way to change the order of appearance of these loads, adds, and stores, because we are trying to write these two lines of code, okay, in RISC-V. if I put both of my loads and then the add to generate my A, okay, the point is after the second load, I need to access the value that I loaded with the x2 to generate my A, right? Because I need to load this, and then add them together, right? And this, at this point, this load will make you at least one stall in your pipeline, because you need to access x2 for which it hasn't known, right, at this point. If I just load the third one, which is F, after the second, so now when I add, so this line will be here. So now when I access x2, I have one instruction in between. So I deferred the execution of the add, because now at this point I have the value of x2 available, so I don't need to put any stalls there, right? Just like this for x4, instead of loading x4 and right away I add it, now I don't have the value of x4. I need to wait for 1 or 3 stalls. So why not I load it before and then add the first one, which is this. So this will give me some space to just make this available and then add it later on, right? At this point, it was available already. So I can just avoid these 2 stalls by just reordering my code. So that's why I reduced 2 cycles from 13 to 11. And that's an optimization. Say this code needs to be run 10 million times. So you have saved so many millions of cycles, right? All right, so that was a high-level view of code scheduling. Okay, let's talk about control hazards. Okay, so control hazards are those type of hazards that normally happen when you want to branch. You want to branch, you want to compare something, and then the values of that you want to compare, one of them or both of them are not available at the time you want to compare these two. So you have to stall them. You have to put bubbles. So how are we going to avoid them, right? So we want to fetch the next instruction depend on the branch outcome. So we want to go either in for or else, or taking the branch or just passing it out and then go for the next instruction. But we don't know the values to compare. And in control hazards, the ID stage of the branch, before the ID stage of the branch, we need to have those 2 values of that for which we want to compare available. So what we're going to do here, okay? Just like what we added in for store and load, for control hazard, we can add another sort of hardware, additional hardware, to just to do it in the ID stage right away for us. Instead of going to the execution, it does it in the ID stage, so we can save one stall out of that. Okay, so here let's have a look. So we are adding x4, x5, and x6. So and right away we want to compare x1, x0, and x40. Actually, this should be 4. Okay. It could be 40 as well. It doesn't matter. 9. Yeah, doesn't matter here. So we are making sure that we want to branch or not. So we want to take the branch or the branch is not taken. And then after that, since we don't know the branch has not been taken, or we are going out of the or we are coming back to the branch, we are doing another comparison here. But for that, we need to wait at least for 1 cycle. Okay. Wait until branch outcome determines before fetching next instruction. Okay. So that's the best case we can do. We add a hardware to do that in ID stage. Okay. With that in your hardware, you need to still be waiting 1 cycle, because at your ID stage, you need to have the access to the outcome of the branch, which was here. Okay, so you need to have one bubble. So this one becomes from here to here, so you can access it. Okay, from the ALU above. So one bubble is still needed. Everyone understood?
So there's a stall because you're waiting for the result of the.
Yeah, because we are not sure if you want to come back, for instance, if it was a while loop, or if you're just going out of the loop, right? We want to continue the rest of the instructions after the while loop. Yeah. So, as well as adding this extra, let's say, path in the hardware to do it in ID stage, okay? And also normally, if you're given such questions, we give you all the information in the question test. Like, for instance, we ask you, like, here is the pipeline, and these are the features that your pipeline have. It has like forwarding or not. The branch can be done in ID or cannot, right? So you have all this information if you wanted to solve such questions. Okay. So another hardware sort of module that can be handy in this to handle like this type of branch hazard is to predict the outcome of a branch. Okay, so this is called branch prediction. So there are so many ways to do a prediction on a branch. Sometimes you can use the history of the branch previously have been done on the same machine to understand, okay, 90% of the time this was a branch, so I can assume that this is a branch. And if you just, so at this point, you're sure that 90% of the time you're right, okay? You don't have to stall. In 10%, you have to pay a price of stalling. Or the other would be do a static branch prediction, right? Always take something and do not consider the other case. In the other case, you just pay the price on that specific instances, right? So there are so many ways to implement this. So in RISC-V, the hardware can predict branches not taken using the history. Okay, and fetch instructions at that point. It's going to fetch the instruction after branch with no delay. So this is a hardware feature that enables you to avoid some bubbles in that specific instance. Okay. But in general, in computer architecture, you have two different ways of branch prediction: static or dynamic. For a static, it's just, for instance, you do always predict that backward branches are taken. Okay. And just like that, you say, okay, I'm gonna assume that all the forward branches not taken. On the cases that this was not correct, you only pay the price for that specific case. You have to install it at that point. Otherwise, if the rest were correct, you are just having the benefit of your prediction, okay, in your system. On the case that you're using a dynamic branch, so you can use sometimes a history, as I mentioned. So you keep a history of all the branches in that specific hardware, and then you say, okay, 70% of the time it was doing this way, so I'm just assume that for this specific case, I'm gonna take that history into account and either take it or not taking it. Okay. So for instance, in the laundry analogy, we must stop taking new loads so that we can restart the load that we incorrectly predicted. So in the case that we missed a branch, we have to stop it, reverse that, and then we pay a price for one stall or two stall, and then we do the rest. Okay? But for the other cases that we were correct, we can just carry on normally. Okay? Was that clear? Do you love pipeline now? All right, overall, the big picture, it is indeed improving the performance, right? It is improving the throughput, the amount of work that you're doing per unit of time or cycle. So because it's going to execute multiple instructions in parallel, although you didn't have any parallel hardware, right? Each instruction has the same latency, so each of them would take the same amount of time. And then you're subjected to hazards, structural hazards, data and control hazard. We talked about it. And the type of the design for the instruction set is going to affect the complexity of your pipeline implementation. So the simpler, the better to handle the hazards. Okay? I'm going to stop here because we can carry on Wednesday the rest of the pipeline. Any questions? So see you guys in the lab in half an hour.